today's topic is exponential and logarithmic functions. Let's start with talking about exponential functions. So exponential functions are any function that have the variable in the exponent. So a simple example of an exponential function would be f of x is equal to 2 to the power of x. Or another example would be f of x is equal to 1/2 to the power of x. In the general form, all exponential equations have a formula that can be written f of x equals a times b to the power of x, where here a represents what we can call the initial amount, so some kind of starting amount, and b, the exponential base, represents the growth factor. So how quickly that initial amount either grows or decays. B, the growth factor, can be any number greater than 0, with the exception of 1, because if we had b to the power, or if we had 1 to the power of x, it would always result in 1, which would make the function a constant. So b can take on any value greater than 0, with the exception of 1. That gives us two major scenarios. One is similar to what I've put over here on this side of the board, f of x is equal to 2 to the x. This would be an example where that growth factor b is something greater than 1. This gives us exponential growth. Graphically, that looks like this. If these are our axes, we have a function that grows sharply as we increase our value of x. Alternatively, we could have a function like the one I've written here, f of x equals 1/2 to the power of x. This would be a case where b is greater than 0, but less than 1. This gives us exponential decay. And graphically, that will look more or less like this. You can see we sharply decay downward. And you can note, looking at these two exponential graphs, that regardless of if we have growth or decay, we always have some kind of horizontal asymptote as part of our graph. That's a feature of exponential plots. Now let's take what we've just learned about exponential functions and do a practice problem. And the practice problem we're going to look at is the exponential growth of bacteria. So let's say that we are in possession of a particular form of bacteria that splits into 2 new cells each hour. So if we start with 1 cell, it will split into 2 each hour. If we start with only a single bacterium in our petri dish, how many bacteria will be present after exactly 1 day has gone by? Let's think about what our given information is here. So for our bacteria growth problem, we know the initial amount, right? That was the single bacterium present in our petri dish. We also know the growth factor. 1 bacterium will split into 2 each hour, so our growth factor is simply 2. Plugging this into the general form of our exponential equation should allow us to then do a calculation. So let's rewrite this general equation as a function of t here, where the t just stands for time, so just reflecting the variable of interest. A is 1, B is 2. So here's our equation. F of t is equal to 2 to the power of t. Now we were told that we want to know the amount of bacterium after 1 day. Let's just remind ourselves that in 1 day there are 24 hours. The bacteria splits into 2 every 1 hour. So if I want the amount of bacteria after 1 day, I'll plug in f of 24 equals 2 to the power of 24, which, as we can tell, is going to be a very large number. It is 16777 bacteria. This problem demonstrates how significant exponential growth or decay can be. So we started with 1 single bacterium. After a mere day had passed with a simple growth rate of 2, we ended up with 16777 bacteria. So quite a large increase in the number of bacteria in the petri dish. Let's turn our attention now to something called the natural exponential function. So the natural exponential function, what is this? This is the function you may have seen before. F of x is equal to e to the power of x. So first of all, what is e? E is a special irrational number, so it's similar to pi, an irrational number. And specifically, e is called Euler's number, and it is equal to 2.71828, etc., etc. So e approximately equal to 2.7. Now, Euler's number, this e, is important for quite a few reasons, and it'll come up quite frequently in equations that you'll use in chemistry. But one reason it's important is because it is the base rate of growth or decay that compounds continuously. So it's any continuously growing or decaying process shares this base factor e. Let's talk a little bit about that right now. So let's talk about continuous exponential growth. So again, this will be used anytime we have a system with continuous change, such as the interest compounded continuously on your savings account, for instance. The general equation for continuous exponential growth is almost always written as follows. F, here I'll call it f of t because we'll be generally working with time, is equal to p times e to the kt. What do all these mean? P, similar to a before in the previous equation, is just our initial amount of whatever is of interest to us. And the k is what we'll call the growth constant. So we have the initial amount, the growth constant, and of course t just represents time. Now that we've got an equation for general continuous exponential growth, let's do a practice problem. And the practice problem we're going to do involves carbon-14 dating. So carbon-14 dating is a method to determine the age of any object that contains organic material. So anything that contains any kind of organic matter can be dated, we can determine how old it is, by measuring the amount of carbon-14 present in the sample. Why is this the case? This is because carbon-14 has a half-life of 5,730 years. What does this mean? So the half-life is the amount of time it takes for the amount of a particular chemical or substance to decay to half of its original amount. So if we started with 1 gram of carbon-14 and we waited 5,730 years later, we would be left with only half of a gram. So using this will help us form our particular problems. Let's look at what the problem we're going to solve will be. An amateur archaeologist claims to have discovered a document that is over 3,000 years old. You know that the document would have contained about 2.4 times 10 to the negative 12th grams of carbon-14 when new. Using modern technology, you're able to measure that there are now only 1.8 times 10 to the negative 12 grams of carbon-14 remaining in the document. Is the amateur archaeologist correct to claim that the document is over 3,000 years old? So there's a lot going on here. Let's take this problem step by step. Let's start by writing out all of the relevant information. So we were told the initial amount of carbon-14 that would have been in this document, and it was equal to 2.4 times 10 to the negative 12th grams. We were not, however, told what the value of K, the growth constant would be. This is going to pose a problem if we want to do our final calculation. So let's take a step 1, which is find the value of the growth constant. So find the value of K. How do we do this? Well, we use what we know about half-life. After one half-life, half of the carbon-14 will be gone. So therefore, if I plug into my generic equation, after one half-life, I would expect my result to be half of this initial amount. So I should get 1.2 times 10 to the negative 12th grams. When I plug in initial amount 2.4 times 10 to the negative 12th grams times e to whatever value k is times one half-life. So the number of years in a half-life are 5,730 years, as we stated before for carbon-14. Now all I have to do is solve this expression to find k. We'll start by dividing over the 2.4 times 10 to the negative 12th grams. This gives me, as expected, 0.5, half the original amount, equals e to the power of k times that half-life. What do we do when our unknown, the thing we want to solve, is stuck up in an exponent? I need to use a mathematical trick here to get it down. And if you're not quite familiar with this trick, be sure to check out the supplemental information for some rules of working with exponential and logarithmic functions. But what I'm going to do is take the natural log of each side of this equation, and I'll talk a little bit more about the natural log in just a little bit. As we'll learn a bit later, natural log and e are inverse functions. So when I take natural log of something with this exponential e, they cancel each other out. And what I'm left with is the value in the exponent. So this will become simply k times this half-life. Rearranging the expression here, dividing the half-life over to the other side, I can get that k is approximately equal to negative 1.20968 times 10 to the negative fourth, 1 over years, so inverse years. Why did I carry so many digits here? I want to make sure that I'm not over-rounding in this intermediate step. So this is just an intermediate step, solving for k. Now that I've got the value of k, I can move on to actually solving the problem I want it to solve. So I'll call this step 2. Step 2. Find the age of the document. So the amateur archaeologist claims it's over 3,000 years old, but using carbon dating, we can find the actual exact age of this document. Let's plug in what we know to our general equation here. So, upon measuring the document, we found that currently it had 1.8 times 10 to the negative 12th grams of carbon-14 left. The initial amount, as we've stated before, was 2.4 times 10 to the negative 12th grams. Multiply that by e to the power of k, which we just calculated, negative 1.20968 times 10 to the negative fourth, inverse years, times however much time has elapsed. Now all we have to do is simplify this and solve. So first step, I'll divide this 2.4 times 10 to the negative 12th over to the other side. That gives me 0.75. Next step, just like before, I'm going to take the natural log of each side. Remember that natural log and e will cancel each other out. So that leaves me on the right-hand side with just the values that were in the exponent. So I've got negative 1.20968 times 10 to the negative fourth, 1 over years, times the time that has passed in years. Rearranging this problem and solving for t, I get a value of 2,380 years. So this is the amount of time that has elapsed since the document was new. What does this tell us? This tells us the amateur archaeologist was not quite correct. The document was not over 3,000 years old, although it was quite old, over 2,000 years. Alright, so we've spent a bit of time now talking about exponential functions. Let's shift gears and look more in depth at logarithmic functions now. We saw logarithmic functions at work a little bit in the previous practice problem, but let's examine them more in depth. First of all, what is a logarithmic function? At the most basic level, we could say a logarithmic function is the inverse of an exponential function. This will make a little bit more sense as we start writing out the general form of logarithmic functions. So let's start with that. So logarithmic functions will have the following form. F of x is equal to log base b of variable x. What does this mean? This means that x is the result or the logarithm of b raised to the power of whatever f of x is. So if I wrote that out in variables, it's telling us variable x is equal to base b to the power of f of x. This is why b is called the base, because it's the base of this exponential form. The most common log bases or values of b that you'll see are 10 and e, that Euler's number that we saw before. And these are often abbreviated, so if we were working with log base 10, you'll often see it simply written as log. Or if we were working with log base e, you'll often see it written as ln, natural log. We saw that in the previous practice problem. Now let's look at the relationship between exponential and logarithmic functions graphically. So first of all, let me draw myself a nice big axes here. And let's remind ourselves of the general graphical form of an exponential function. So let's say we have exponential growth. My function will look more or less like this, sharply increasing function. Let's say this is a graph of f of x is equal to e to the x. This function should have an inverse, which is its reflection across the line f of x equals x. So if I reflected this across f of x equals x, what would it look like? It would look more or less like this. A function that sharply increases and eventually levels off. This is the graph of f of x equals natural log of x, so log base e of x. Therefore, you can clearly see here this exponential function e to the x and this logarithmic function, natural log of x, are inversely related. You can also note here that whereas the exponential function has a horizontal asymptote, the logarithmic function has a vertical asymptote. So now that we know what logarithmic functions are, let's think really briefly about why they might be useful, particularly within science and within chemistry. So logarithmic functions, first of all, you've seen that they're useful in solving different equations, so we can use them to help simplify equations, solve for certain variables. But they're also often a useful way to report information, to report scientific data. One that you've already seen is pH. So let's talk a little bit about pH and why it's important logarithmically. So hopefully you remember the equation pH is equal to negative log times concentration of H3O+, the hydronium ion. So this basically tells us as we increase the concentration of hydronium ion, we will decrease the pH. Let's say, for example, we have a strong acid, like HCl, and we put it in water. We know this strong acid will fully dissociate, and what we'll end up with is hydronium ions, and in this case, chlorine ions, with the same concentration as the original HCl. If we were interested then in tabulating or graphing the different concentrations of HCl, we could get things like this. We could say 0.1 molar HCl, which of course would give off 0.1 molar hydronium, or we could go and make a solution of 1 times 10 to the negative 5th molar HCl, which would give us 1 times 10 to the negative 5th molar hydronium, or so on, with different concentrations. Here I'll write up 1 times 10 to the negative 9th. Graphing this data, we can see, would get a little bit difficult because we're working with increasingly small values. If, however, I instead switched to a logarithmic scale, using the pH equation here, these numbers would be much more reasonable. This would be simply 1, so 0.1 molar solution would give a pH of 1. A 1 times 10 to the negative 5th molar solution would give a pH of 5. And a 1 times 10 to the negative 9th molar solution would give a pH of 9. So here we have much simpler numbers to work with. This shows that occasionally logarithmic scales are much easier to work with than exponential ones. Be sure to check out the supplemental information for some tips on working with exponential and logarithmic functions. But thank you very much for watching this Yellow Rabbit Mathematics video, and I'll see you next time.